All right, so the next thing we want to look at in our list that we're working through right now in this current series of videos is another type of symmetry. I don't have it listed here in the bullet list, but it kind of falls under even and odd signals. It's another type of symmetry associated with complex valued signals called complex-conjugate symmetry. So here's our definition that we're going to examine in this video here. We talk about complex signals, and it's a property that complex signals may or may not have. If a complex valued signal x of k has this property right here, namely that x at time minus k is equal to the conjugate of x at time positive k, if this equality holds for all discrete time k, then we call that signal x of k a conjugate symmetric signal. Just to refresh your memory, what this symbol right here means, a little asterisk, that means complex conjugation. So for example, if we had a complex valued discrete time signal x of k that had a real part of a of k and an imaginary part of b of k, note the j right here makes that whole term right here a complex quantity. When we take the conjugate means replace all j's with minus j's. So if this is the definition of x of k, having taken the conjugate, everywhere I had a j, I replaced it with a minus j. In this particular example, the only place I had a j was this one spot here. So having changed that to a negative j, I now have a of k minus j b of k. So this is what the complex conjugate operation does for us. We're going to look at an example here in just a minute, and what we're going to find, we're not going to prove it, but what we're going to see is that if I have a complex conjugate symmetric signal, what that means is that the real part is even, which we just discussed in the previous video, and the odd part, and the imaginary part is odd. So one way to check if a signal is complex conjugate symmetric or not is to examine the real part, make sure that it's even, examine the imaginary part, make sure it's odd. If both of those hold, then you can declare that that complex valued signal is a conjugate symmetric signal. If either of those fail to hold, then obviously you don't have a complex conjugate symmetric signal. All right, let's go ahead and look at an example here. So here's the example we're going to work with. We're going to work with x of k equals k squared plus j times k. So obviously this part right here, the k squared term, is the real part of the signal, and the k part right here is the imaginary part of the signal. Let's go ahead and just plot and examine first the real part. So k squared, when k is 0, 0 squared is 0. When k equals 1, 1 squared is 1. When k equals 2, 2 squared is 4, 3 squared is 9. So I get very much this kind of polynomial growth thing going on here. When k is -1, a -1 quantity squared is 1, and -2 quantity squared is 4. So I get negative values that look like this. And indeed, you can tell now by looking that this is an even signal, right? Whatever value I have at positive time is the exact same value I have at negative time. So this is indeed an even signal. Let's go ahead and look at the imaginary part now. So there's my time axis. And again, remember the imaginary part is just the line k. So when k is 0, it's 0. When k is 1, it's 1. At k -2, it's -2. So I get this line with a slope of 1. And again, just by looking at this, you can now see that this is indeed an odd signal. Whatever value I have at positive time, I have the negative of it at negative time. So this is indeed an odd signal. So if you go by the rule that we had in our definition, if we have a real component that's even and an imaginary part that's odd, then x of k as a whole must be a conjugate symmetric signal. So we can go ahead and conclude that this example we're working with, x of k, is indeed a conjugate symmetric signal. We can also do a final computation to make sure that that holds from scratch in terms of our definition of x at time minus k is equal to the conjugate of x at time positive k. So we can do that pretty easy just by doing a direct computation. So let's actually compute x at time minus k. So to compute x at time minus k, I know what x of k is, so all I have to do is replace every k with negative k to evaluate x at time minus k. So let's do that. I replace k with minus k, replace this k with minus k. A minus k quantity squared is obviously just k squared, and I end up with this. So this is what I have for the time reversed signal x of k. Let's also directly compute the conjugate of x of k. So remember, to take the conjugate, I look here, everywhere I have a j, I replace it with minus j. That's pretty simple to do in this example because there's only one j. So at k squared stays by itself because there's no j's there, but the j here gets changed to a minus j. So I have now directly computed what x conjugate of k is. Remember our definition of complex conjugate symmetric. I need these to be equal if I have a complex conjugate symmetric signal. And indeed, if you look at these two quantities, the first one is k squared minus jk, and this one is k squared minus jk. They are obviously equal to each other. So we have now worked an example of a complex conjugate symmetric signal. It was a complex valued signal. Because it's conjugate symmetric, its real part was even, its imaginary part was odd. Obviously, we could come up with an example that was a complex signal that failed having one of these properties, and then it would not be a conjugate symmetric signal, but we'll have to save that for another example. In the next videos, we'll keep working through our list of signal properties. See you then.